Chapter 8.6 is about power series. Here's a quick outline. We'll talk about the definition of power series. We'll talk about where power series converge, what values of x make them converge, both the radius of convergence and the interval of convergence. We'll talk about taking derivatives and integrals of power series, and we'll talk about solving differential equations with power series. Here's a quick example of a power series, or kind of our generic power series. That's a 3x cubed there. So you can see we've got powers of x multiplied by some coefficients. So if we want to compress this writing into a summation symbol, how would you write like the thing down here below it, the thing up here above it? What would you write over here? Take a sec to think about that. Well, we apparently have a0, a1, a2, so we might write a sub n, and n would start then at 0 because we need to have an a sub 0. So we'll start at 0, go up to infinity, and each time I have like a sub 2 is multiplied by x to the 2, a sub 3 is multiplied by x to the 3, so I'd have times x to the n. Now that might be a little odd because this x doesn't have a power on it, but of course we could say it has a power of 1, just like a sub 1, and we don't even have an x here, but you could say, well, that's like x to the 0. So that brings up the issue of, what if I put in x equals 0, then I'll get 0 to the 0, which is technically undefined. So we're going to say in this chapter that 0 to the 0 counts as 1, not undefined. That just makes life easier. So that's the way we write a generic power series, either in the kind of long version or the summation notation. So one thing we need to point out here in chapter 8.6, our default starting point for n for a power series is 0 rather than the 1 that it was in chapter 8.1 through 8.5. And a lot of textbooks do that. They start with defaulting to n equals 1 to start, and then when we get to power series, they default to starting at 0. So that's something good to keep in mind. A few other things about power series. Are they polynomial? They sure look like it, but polynomials technically can't go on forever. They have to have a single last or highest power term, like x cubed in this case, without the plus dot dot dot. So they work a lot like polynomials, but they're technically not a polynomial. The a sub n here is the coefficient on x to the n, which means that the a sub n should not involve x at all. All of the x stuff should be put into the x to the 1, x squared, x cubed, etc. So is this an acceptable way to write? So it will have different formulas for different power series for a sub n, but is this one acceptable? No, because it has an x in it. So that's not allowed. How about this one? 1 over 2n factorial x to the n. Well, the terms are something times x to the n, but that's not the a component. The a component should just be 1 over 2 to the n in this case. So saying a sub n equals 1 over, 2n factorial. I said 2 to the n, but I meant 2n factorial. So that's how you would write a sub n, and then the x to the n is just taken care of by this part of the summation. We have to remember that in chapter 8.1 through 8.5, a sub n was our sequence of terms to sum, but now we're saying it's just the coefficients on the x to the n, and the term to sum is actually a sub n times x to the n. So that's another thing to remember. And another thing that sounds like something I said before but isn't really, that if I don't specify what an a sub n is, like if I don't say what a sub 3 is, that defaults to 0. So that's saying what the coefficient defaults to, rather than saying where the coefficients start at n equals 0. And this will be important because a lot of series that we'll do will have like every other term in use and every other term not in use. So we'll have a default of 0 on every other term. Next, we'll try writing out some power series to get used to the idea.